I'm going to talk in the 5 minutes I've been given about a project that I'm doing in collaboration with Jeff Manley's group at UC San Francisco. They actually work at SF General, where Jeff is also chief of neurotrauma. So I have meetings where my collaborators go out, pull some pieces of cranium out of someone's brain, and then come back 20 minutes later and continue as if nothing had happened. So the work is funded by Intel Digital Health Group with matching funds from UC Discovery, and we've been doing this for about a year now. So in case you haven't been to one, this is a modern intensive care unit. There is a patient just there. You can just see a little bit of the patient. If you have a chance, Atul Gawande wrote a very nice article in the New Yorker a couple of issues ago about intensive care. So it's probably the best layperson's introduction to what the real world of the intensive care unit is like. One of the things he points out in that article is that on an average day, on an average patient in the intensive care unit, 180 medical procedures are carried out. The total cost of intensive care in the US is $280 billion a year, which is larger than the entire worldwide semiconductor industry. So right now we have, 1.5 departments on every major campus in the US covering, just the semiconductor industry, more or less, right? How much do we have covering intensive care industry in terms of doing the research required to make this efficient? Not very much. I was talking yesterday to Princess Sumaya of Jordan, who was visiting, and I pointed out that a 20% improvement in the efficiency of this would equal the GDP of Jordan. So, okay. So as you can see, there's lots of equipment in here. Some of this is keeping the patient alive. There's ventilators and drips and all kinds of stuff. But a lot of this is monitors. So the patient has about between 20 and 40 real-time sensors inserted in through arteries into the heart, drilled into the brain, stuck into the muscle. They're kind of wired up with these things. And all these monitors, to a first approximation, the data is warming up the walls in the ICU because the data goes up on the screen, the electromagnetic radiation goes off into space and warms up the walls. Okay? About once a day, the nurse takes the notes that she's written on paper and gives them to the doctor, who then puts them onto a little 3x5 card. And that's the state of the art in the typical intensive care unit in the US. So what we're trying to do is to collect this data, and Jeff has put over $1 million of funding, 7 years, 4 IT consulting firms, just to get to the point where he can collect all the data and put it into a database. Because, as was mentioned before, the people who manufacture all these sensors and this equipment absolutely hate the idea of anyone collecting the data, because that means they don't get to have a monopoly on the equipment and its use. So the patient comes in. There's about 140 fields in the initial presentation record. There's up to 40 real-time sensors, so vascular measurements, pressures, intracranial stuff, temperatures, electrical, gas exchange, all the ventilator readings. And then there's about 1,500 different kinds of pieces of information that are gathered asynchronously or provided asynchronously. So everything from fluids and blood tests and measurements, the care events, all the things that the nurses do to the patient. Lots of stuff just recorded in text, which is a bit of a nuisance. And over 1,000 different drugs that are used in the intensive care unit. And every administration of every drug is recorded. So given that data, we want to compute the posterior probability distribution for what on earth is going on inside the patient. So when I first went, the first meeting I had with Jeff and his collaborators, what we agreed on was the following metaphor, right? That these patients are inside an unknown maze in complete darkness, right? Somewhere, by and large, there is an exit to that maze, and there is a route to that exit. And what we're trying to do with this is to turn the light on. Okay. The next stage is then to plan the route to the exit, but that's another project. That's a planning project. This is really a state estimation project. And the method we're choosing is to use dynamic Bayesian networks, which is a parabolic technology, and that the fact that it's parabolic and not a classical dynamical systems model is really important for reasons that we'll see. It's also very important that it be patient adaptive. Okay, there are no two human beings that are identical, and it's no good taking a deterministic model of some idealized human and applying it to data coming from a natural human, because instantly the data and the model will disagree, and then you've lost. Okay, so we have to have the model adapt to the patient and cope with the uncertainty generated by the data. So I'm not going to go through every detail of this slide. This shows at a very high level the geography of our model of human physiology. And so there are 13 major subparts to this model. And when it's completed, it'll have about 1,000 state variables. I'll just show you one little piece, and I'm not even going to show you very much of that. So I have to use the... You can see this very well. Okay, so these are variables talking about this whole thing is the control that the brain exerts on the vascular system. So how does the brain cause your blood pressure to go up and down and your heart rate to go up and down? So there's a medullary control center up here. It works through 2 parts of the nervous system. These are 6 different neurotransmitters. And then these are variables like the contractility of the heart muscle and the vascular tone. So the blood vessels actually have muscles around them that cause them to that can relax or squeeze to change the resistance to flow of the blood. And then down here we have things like the mean arterial blood pressure. So these are random variables. Each circle is a random variable describing some aspect of the current state of the patient's physiology. And this is just one part of one of those 13 components. And this shows, okay, so at the next time step, so this is at time 1, this is at time 2, and there's actually a very straightforward connection. There are things called baroreceptors that the brain uses to figure out what its own blood pressure is, and then that signal is fed back into the medullary control center. Okay. So here are some of the other parts of the model. I think we just... Okay, these are the sensors, and here are some drugs. And I'm afraid that the one key part of this, whatever color it is, the monitor completely ignored it, so you can't see it at all. But never mind. So in all of these spaces, like here and here and here, all those spaces are the connections to the other parts of the physiology. Okay, so this is just one part. This is one part of the vasculatory control system. And then there are lots of connections from other parts of physiology into this and from this to the other parts of physiology. Okay, so that's one part, right? We have a large parabolic dynamical systems model of physiology, and then we take the data coming in through the sensors, and we compute from that the posterior probability of the hidden variables in the model. Okay, so here's why we need both parabolic models of dynamics and parabolic models of the sensors themselves. And that's because, number one, we don't know dynamics perfectly, particularly for an individual patient. And number two, the sensors are incredibly noisy and full of all kinds of weird behavior. So this shows, on the top we have the blood pressures. So the pink range shows the range between diastolic and systolic blood pressure, and then the mean is the red line running through the middle. We have the blue is the heart rate, and down here we have some more pressures. This is central venous pressure, this kind of blue line. You can see that at various points along the way, the central venous pressure reading just disappears. And that's because the central venous sensor is kind of difficult to get it to work, and sometimes it just starts to return nonsense. Okay, up here, this blue line that's very near the top, that's the blood oxygenation level. And again, in lots of places along here, it just disappears. And from here, the central venous line just stopped working altogether. Okay, so this is very common. Down here, we have the ventilator variables. And you can see that, so let's look at this kind of coffee-colored line that seems to be sort of jumping up every so often. So this is called the compliance. This measures how stiff the lung is when you try to push air in it, how much work do you have to do to get that air in there. And when the compliance is going up, right, that's supposed to mean, according to what compliance is defined as, that all of a sudden it became much easier to push air into the lung. Okay, what's actually probably happening here is either suctioning, which is when they stick a tube down which goes inside the ventilator tube and into the lung to remove mucus from the inside of the lung so that the ventilator tube is less obstructed. Or it could be that the patient's coughing. When the patient coughs, the readings from all the ventilator variables go pretty haywire. Okay, so when I first started working with the clinicians, they kept saying, "Oh, don't look at that data. That's all messy. You don't want that. Let me clean it for you by hand. One data point at a time, and there's 50 gigabytes of data that we have in our database. Let me clean it for you, and then you can look at that. Because I know that modeling people only like clean, perfect data with no artifacts and no noise and no dropouts and so on." And I said, no, you're missing the point, right? We can't do this with clean data because clean data doesn't come out of the monitors in real time in the ICU anyway. And the other point is that with probabilistic modeling, we really want to see the dirt because we have to model the dirt in order to get to the truth. Okay? So let me just show you how we model some of the dirt. This is a model of how blood pressure readings are generated. Okay? So if we go back to this slide here, if you look up on the blood pressure trace, okay, you'll see various spikes. So here, apparently, the patient's blood pressure dropped to 0. Okay, does that mean he died? Actually not. No, what it means is that they were recalibrating the blood pressure monitor, which they just turn a little tap on the arterial line to expose the transducer to the air pressure, and then they set that to 0. Okay, so while they do that, you're reading air pressure, which is defined to be 0, and not the blood pressure. Okay, and then there are these spikes. Spikes going up, where apparently his blood pressure went to 300 in various places. Here about 250. Okay, so his blood should have been streaming out of his eyeballs and you name it, right? So was that happening? No. This is when they were doing a blood draw. And when they do a blood draw, they turn the little tap on the arterial line. And when they do that, the transducer is exposed to the pressure from the bag. There's a high pressure bag that stops blood from leaking out of the patient. Okay, and that bag is at least supposed to be at 300. Okay, and so you're seeing for some period of time a reading that's much higher than the patient's actual blood pressure. So we model all those kinds of events. So we have events, random variables, that talk about during the interval of measuring, which is actually a 1-minute interval, what fraction of that interval will we expose to the atmospheric pressure? What fraction will we expose to the bag pressure? Okay. Now don't forget, we don't know what the bag pressure is. Right? So that's another random variable in model, and we'll actually see that the system is able to estimate the bag pressure from these artifact readings that we're getting from the patient. So here's one trace, right? So this here's the systolic, mean, and diastolic blood pressures, and all of a sudden they start spiking up. Okay, and this is over here about a 3 or 4 minute period. So what actually happened, and what's correctly inferred, was that in the first minute, okay, this talks about the fraction of the minute that the transducer was exposed to the bag pressure, right? So in the first minute, about 50 seconds of that minute, we were exposed directly to the bag pressure. And then we went back to ordinary blood pressure, and then another blood draw was taken, okay? And that second blood draw overlapped some of the interval. And so in the second and third minutes, there was also blood draws, okay? And that's why you get this sort of a big hump and a little hump appearance. And you can see that the brown line marks the inferred blood pressure, and you can see that the system not only detected these events, but also correctly inferred what the blood pressure was during those events. Okay, so the brown line shows that we get rid of the artifact completely. And here's a little 2-day period just showing all of these excursions of blood pressure. Every time you go over 180, the alarm sounds in the ICU. And if you read Gawande's article, he'll remark on how annoying it is to have these alarms going off all the time. And after we apply our methods, so now looking at not the measured blood pressure, but our posterior estimate of the blood pressure, all of those alarms go away, with the exception of these ones, which actually turn out to be real alarms. Right? So these were not artifacts, but these were real. Okay. So to sum up, This is going to be a big project. Building a model of all of human physiology is not easy. It's not as hard as you might think. In 1972, a guy called Guyton at the University of Mississippi actually built a 354 state variable model of a pretty big chunk of physiology, so circulation, renal operation, heart, and so on, and was able to show that that could give you quantitatively accurate predictions over multiple weeks. It could tell you what will happen if you remove this patient's kidney and things like that. So it was pretty amazing, but it was a deterministic model, and they had no idea what sensor modeling meant. And so there was no way to use that model on an individual patient. All you could do was run simulations and get qualitative impressions from the simulations of how things were working. Okay? So this is a different kind of technology for modeling, and it has a more direct application to individual patients. Okay, I'll stop there and take questions.
Obviously, that's a very sophisticated heuristic model that you develop. What would be the relative benefit over and above using the technologies that say we really don't know what's going on, for example, linear predictive analysis or a neural networking approach, where over a period of time the model sort of self-learns a little bit about the patient?
Well,
or is that a fair question?
So a linear predictive model, if you believe that human physiology is linear, then that would be a good model. But human physiology is not linear. So even Guyton's model in 1972 had many, many, many nonlinear components. There's lots of saturation, right? Linear models say that your blood pressure can go to infinity or minus infinity, right? Doesn't happen. So there's lots and lots of nonlinear stuff. So neural networks don't really they're not really a dynamical systems model. So all they can do is map directly from data to data sequences. They don't represent the underlying state of the patient. So they're a different kind of technology, and they haven't proven capable of analyzing this kind of data.
So you have 50 gigabytes worth of archival data that can develop the parameters that you need to drive your model. I was just thinking that might be a useful approach to look at which of those are the most sensitive and which are not sensitive. I'm sure that's part of what you're trying to do.
Yeah, so I mean, and Guyton did a lot of that too, and he found that a lot of parts of the model, you could change them by a factor of 10, and the gross physiological sequences ended up being pretty similar. And that the human body has to be designed that way, right? It can't rely on the fact that you have exactly 11.2 grams of cornflakes for breakfast every morning, because that isn't how it works. So a lot of the model, right, the quantitative information for building the model is already available in the physiology literature. The literature doesn't often give you good information about the variance, and so what we're doing with the data itself is actually using that to get a better idea of the variance, how patients' parameters vary across the population and across time. Good question.
Stuart, I had an interesting conversation with somebody from the FDA who was looking at closed-loop systems, and he said these sorts of any sort of system that uses some sort of learning approach are very difficult for them to test. And I imagine this is also might fall in that category because it's very patient-specific. How would testing or validation of the model work on a patient-specific basis for such a model? And could it be used, for example, in simulating in training programs for residents and those sorts of things? So maybe there are two questions there. One is the testing, and one is the simulation for an applicability for training.
Yeah, it could certainly be used in simulation, and I think for training. So one of the important things about training is specifically for the students to learn how the individual patients vary and how to figure out from what's going on the properties of the individual patient. So we can show that very graphically. You can look at the variance of your initial estimate for some property of the patients, like the total vascular resistance, and then you can see that as we get the data, you can see the variance of your vascular resistance estimate going down to something close to 0. So testing, and FDA approval. So FDA approval, I don't know exactly the rules. Right, this is not an implantable device.
I'm sorry, I shouldn't have started with the FDA. I only mentioned that because it came out in the context of FDA. I was more interested in if the model is very patient-specific, does that have implications for the way it's tested?
Well, so what you do for testing is what you do for testing is you want to, in some sense, simulate the application of the system in real life. So what do you do with a system in real life? You get a patient that you haven't seen before, but after you've been running the system for a while, now you've seen a few hours of that patient. How well are you doing? So what we would do, we'll hold out a set of patients, and then for each patient hold out a set of time and see how well we can, for example, do prognoses. We can estimate the onset of sepsis or multiple organ dysfunction syndrome, MODS, or ARDS. So all these kinds of major causes of death in the ICU, and detect their early onset, perhaps the location of infection, things like that.
How real time is your algorithm right now?
Right now it's quite a lot faster than real time, but that's because the model is quite a lot smaller than the whole model. And that's the last point here. Until we have the whole model, so the algorithms are Monte Carlo algorithms that we've actually developed over the last 14 years. So they work pretty well for robotics applications. People have been using them for state estimation in 100,000 dimensions. So I think there's some reason to be optimistic that they will be able to scale to the whole model. If not, I have lots of hardware people who'd be only too happy to build special purpose hardware. And we have lots of algorithms people, including our own group.
Question here?
Yeah.
Let's say you apply these to multiple patients. Can you then pattern match and compare, and that way you don't have to reproduce this whole state space every time you analyze a patient, but you can sort of reach different points in state space and quickly find your answers?
Well, yeah, I mean, that could be a way to do it, that you would, instead of trying to model the new patient, you would just say, as they do with weather forecasting, they just say, well, what's a week that looked just like this week, and then, well, what happened on Wednesday, and make that prediction. There's a huge amount of variation. So we have well over 1,000 patients in the database, but my collaborators seem to be able to remember every single one of them. And they'll say, oh, well, what about that guy who fell off a ladder and had an epilepsy?
So the answer is yes, you can identify the patterns of behavior. In effect, if you...
Well, no, I mean, say they remember them because they're all different, right? They're all,
sure.
And so there might be just too much variation in there to get useful predictions from a previous patient. But it's certainly a good approach, right? What we're really doing is we're saying, okay, what's the best way to implement a mapping from a gigabyte of data collected from a patient to an assertion about the internal state of the patient or about the future of the patient. Okay, and that mapping can be implemented, as you said earlier, by a neural net, by convoluted ARMA model, by lots of things. But our belief is that by physiological modeling, we're able to get much more accuracy and much more understanding of what's going on in the patient. It's a belief that has yet to be really tested. But just looking at what's happening with the sensor data, I don't know of any other system. So all these commercial ICU monitors, I mean, they have built-in data filtering algorithms that are supposed to not sound the alarm when there are artifacts generating spurious data. But there isn't any system out there that's able to correctly identify blood draw artifacts and filter them out because they vary enormously, right? A blood draw that takes 10 seconds and one that takes 50 seconds look entirely different when you look at the 1 minute blood pressure average signal. Some of the artifacts go on for 45 minutes. So there's something called mucomist, which is a kind of a bottle that you plug into the ventilator circuit that gives this mist that tries to clear out the lungs. And that changes the ventilator readings by 40%. and that goes on for 45 minutes. So there isn't any sort of simple, remove any number that's over 200 kind of algorithm for data filtering. So I don't know of any other way to do this besides model-based methods.
Thanks.